we're going to be taking a look at problem 941, valid mountain array. This one is a Leetcode easy taken straight off blind 75, and it deals with arrays, so it should be relatively simple and straightforward. Taking a look at the problem, we're going to be given an array of integers called r, and we need to return true if and only if r is a valid mountain array. So what constitutes a valid mountain array? Well, first, the array length has to be greater than or equal to 3, and second, there has to exist some I value between 0 and the length of the array, non-inclusive, such that all of the values before I are strictly increasing and all of the values after I are strictly decreasing. So before we go ahead and unpack that second problem bit, let's go ahead and take a look at the first because it's super simple. We need to make sure that the length of the array is greater than or equal to 3. So we automatically know that if the length of the array, if r.length is less than 3, this cannot be a valid mountain array, and we'll return false. All right, with that out of the way, let's go ahead and take a look at the second part of the problem, the more interesting bit about the existence of some I value before which all values are strictly increasing and after which all values are strictly decreasing. So if we wanted to go ahead and sort of visualize this, we can go ahead and start by visualizing some sort of point, which we'll call I. So this will be our point, I. And all values before I are strictly increasing. So we increase up to I. And then after I, we strictly decrease. So we go all the way down. Now, the view that I drew is relatively symmetrical here. It doesn't need to be. We can have an I with very few numbers before it and very many after it, or vice versa. It really doesn't matter. Now, what we do want to make note of is that an invalid mountain array will have more than one peak. So here we see that there is exactly one peak. An invalid mountain array where you maybe say strictly increase up to some value and then start decreasing, but then increase afterwards again and then decrease afterwards again, that is always going to have more than one peak. And so what you'll notice is that if we start climbing the valid mountain array from the left, if we have some sort of climbing system and we go value to value while it's increasing, we'll hit this peak right here. And if we do the same from the right, if we climb backwards from the right, we'll also hit that exact same peak. And that's not the case for the invalid mountain array. If we start increasing from the left, we're going to hit this peak right here. But if we increase from the right, we're going to hit this peak right here. And so what we can do is sort of simulate this behavior from both sides of the array, and we can check whether or not our climber on the left side and our climber on the right side met at the exact same peak. If that is the case, then we do have a valid mountain array. Otherwise, we don't have a valid mountain array. All right, so if we want to go ahead and code this out, it should be relatively simple. In order to represent our left climber and right climber's position, we'll go ahead and use integers as indices. We'll start the left climber off at 0, the very first element, and we'll start the right climber off over at the very last element of the array. Now, we want the left climber to climb while there is something to climb, while the face in front of him is increasing. So if the current position is less than the next position, if the next position is higher up, then we want to increase the left position. Similarly, we want to do that with the right, except this is a little bit trickier because from the right we have to move backwards. So you'll notice that if we move backwards from the right, if we are currently at some r value right here, then at the value r minus 1 here, the r minus 1 value is actually going to be greater than the value at r. We can write that out pretty simply. While r is less than r of r minus 1, we want to, like I said, move backwards. We want r to move backwards up the mountain. And lastly, we want to check whether or not the left and right position are at the same peak. If L equals R, then we know that this is a true valid mountain array. Otherwise, it's a false mountain array. It's not valid. Now, this covers almost every single edge case except for one. Remember, I has to be between 0 and the last element of the array non-inclusive. So we can't have our left climber start out at the peak and have our right climber just move up that mountain. Similarly, we can't have the opposite case where we start the right climber off at the peak and have the left climber move up. And so in order to check for that, we can do a variety of different things. But the easiest is probably just going to be a simple check after we increment the value of L or decrement the value of R. So if L now becomes equal to the very last element, then we know that this can't be a valid mountain array, and we want to return false. Because of this second case, L moved up all the way to the very last element. That's not a valid mountain array. Similarly, we can just go ahead and copy and paste this line. If R is equal to 0, if R is the very first element in the index, we return false because of this case. R has moved to the very first value. And this should work. But I'm not going to go ahead and submit the solution like this because there is a way to minimize the amount of lines that we've written here. You'll see that in addition to incrementing and decrementing L and R respectively, we also do this check. It turns out that we can go ahead and use the precrement operator in order to condense both of these lines into a single line. The way we're going to do this is super simple. Basically, all we want to do is increment the value of L before we run through this if statement. And so we can do that using the precrement operator, and we can do that for R as well. All right, and with that out of the way, we can go ahead and submit the solution, see if it works. Yep, and indeed it does work. So this solution runs in O of n time, where n is the number of elements in the array. That's because we loop through this array just once. And the space complexity is going to be O of 1, constant time, because all we do is create 2 new integers, and we don't create any other sort of data structure. All right, so that is it for problem number 941, valid mountain array. Hope this helped.